Hello students, welcome to the first session of D and F block elements. In this session, we'll discuss about the D block elements, the definition of D block elements, the general electronic configuration, why D block elements shows horizontal similarity, the reason for the typical characteristics of transition metals, and we'll also look into the trends in their metallic character. Okay, let us begin. First, let us look into the position of D block elements in the periodic table. You can see that it has been placed in between the S block and the P block. Since it comes in between the metals of S block and the non-metals of P block, therefore the D block elements are known as transition elements. In the D block elements, the electron enters last but one shell, that is penultimate shell. This results into four horizontal rows which are known as 3D series, 4D series, 5D series and 6D series. In the case of D block and F block, in F block there are two series, namely 4F and 5F series, which are known as lanthanides and actinides respectively. In both the D block as well as F block, the last electron does not enter the ultimate shell. Last electron does not enter the ultimate shell like S and P block elements. In case of D block element, it enters the penultimate shell, that is last but one shell. And in case of F block elements, it enters anti-penultimate shell. Therefore, the number of electrons in the outermost shell of D and F block elements are almost same along the period, that is along the horizontal rows. Hence, they tend to show horizontal similarity. You would remember that we always studied S and P block elements within a group. That is, S and P block elements shows vertical similarity. Again, it is because of similar electronic configuration within a group. In case of S and P block elements, the last electron entered the last or the ultimate shell. Whereas in case of D and F block elements, the last electron does not enter the ultimate shell. In case of D block elements, therefore, D and F block elements tend to show horizontal similarity. They tend to show horizontal similarity. In case of D block, if N is the last shell, then in case of D block, the last electron enters N minus 1 D subshell, that is anti-penultimate shell. Okay, that is why D block and F block elements shows horizontal similarity. Now let us look into the definition of D block elements. D block elements are those elements in which the electron enters D subshell, in which the last electron enters D subshell. Now let us look into the definition of transition elements. Transition elements are those elements which contain incompletely filled D subshell, either in their ground state or in their most common oxidation state. Based on the definition of transition elements, there is a question: why zinc, cadmium and mercury cannot be considered as transition elements? Zinc, cadmium, and mercury, although included with D block elements, are not transition elements because it does not come under the purview of the definition of transition metals. As per the definition, they must have incompletely filled D subshell. But zinc, cadmium, as well as mercury, both in their ground state as well as in their most common oxidation state, which is plus 2, does not contain incompletely filled D subshell. Rather, their D subshells are completely filled both in the ground state as well as in their most common oxidation state, that is plus 2. Hence, they cannot be considered as transition elements. Okay? General electronic configuration. General electronic configuration of D block element is N-1 D1 to 10, Ns 1 to 2. You can see that this general electronic configuration may not be exactly followed. For example, in the case of chromium and copper, the expected electronic configuration of chromium is 3d4 4s2, but the actual electronic configuration is 3d5 4s1. Similarly, in the case of copper, the expected electronic configuration is 3d9 4s2, but the actual is 3d10 4s1. What is the reason for exceptional electronic configuration of chromium and copper in the first series of transition elements? The reason is half-filled and fully filled electronic configurations have extra stability due to greater exchange energy in these configuration. There are various characters of transition elements which are typical of it. For example, transition elements shows variable oxidation state. It is capable of forming colored compounds. It forms complexes, can be used as a catalyst. Most of the transition elements are paramagnetic, and the most important feature, they show horizontal similarity. Now, what is the reason for that? What is the reason for the typical characteristics of transition elements? If you look into the shape of d orbitals, which is a double dumbbell shape, we can observe that the d orbitals are far from the nucleus and closer to the boundary. D orbitals are far from the nucleus and closer to the boundary of the atom. Hence, they interact with their surrounding. Apart from that, due to partially filled D subshell and low difference in the energy of N-1 D and Ns electron, these elements show a variety of characters which are typical for them. Now let us consider some of the general physical properties of transition elements. If you are asked to think about a metal, what comes into your mind? Obviously, it will be iron, copper, silver, gold, etc., isn't it? And you know all of them are transition elements. You don't think about sodium, potassium, rubidium, etc. Although you know that they are alkali metals or even alkaline metals, does not come into your mind. Why? Because when we think about metals, we think in terms of their properties because they have very high metallic bond strength. We can say that most of the transition metals are typical metals with high melting and boiling point. They are good conductors of heat and electricity and have high thermal and electrical conductivity. But there are exceptions, that is, zinc, cadmium, and mercury. Now, if you look into the graph showing the melting point of the transition elements, the melting point increases up to D5 electronic configuration, except for the anomalous value of manganese and technetium, and then it falls as the atomic number increases. If you look into the enthalpy of atomization, you will see that enthalpy of atomization is also high for the transition metals. It also reaches its maximum at the middle of each series. This phenomena can be explained on the basis since n-1d, that is penultimate d subshell, and the ultimate s subshell, electrons have almost same energy. N-1d and ns electrons have almost same energy. The unpaired n-1d electrons participate in interatomic interaction, thereby increasing the enthalpy of atomization and the melting point. That is because the metallic bond becomes more stronger due to these interactions. Both enthalpy of atomization and melting point is affected by the strength of the metallic bond. Remember, enthalpy of atomization is an important factor in determining the standard electrode potential of a transition element, which in turn is responsible for the reactivity of the metal. Those elements which have high atomization, which have high enthalpy of atomization, tend to be less reactive and more noble in their behavior. This is a very important point. Elements with high atomization, enthalpy of atomization, tend to be less reactive and more noble in their behavior. Also, important point to note is that metals of second and third series have greater enthalpy of atomization than the corresponding elements of first series. This is due to more metal-metal bonding in heavier transition metals. So the metallic property is actually reflected in melting point as well as enthalpy of atomization. Okay.